Indiana John, you are number one. Good morning. It's morning somewhere. How are you? Murphysville, welcome. Dika, welcome. Welcome aboard. Hey, Barzy. Good morning, sir. Or, yeah, it is morning for you. Triple caution. Howdy, neighbor. Ed Kramer, welcome aboard. Hey, Adam, welcome aboard. Hey, Stan, you know, I'm sitting literally from my nose. It's 27 inches to a Hotshot 360, which I'm enjoying very much. On the way back to New Hampshire from Kansas. Wow. Hi, Ed. How are you? Well, we got a good crowd early. That bodes well. So if you guys are just tuning in, we're going to have a guest later. Oh, you visited with Tom. I'm representing today. That's awesome. Proteum Machining, welcome. Chris, welcome. Golden State Innovations, welcome aboard. Fad Radcator. Now the party could start. Welcome aboard, guys. It is a gorgeous day here. Yes, it is a gorgeous day here in the New Hampshire. Sun is shining, and temperatures are coming up. Yeah, we should talk, Stan. I have, let me, this is for Stan. This is for Stan's edification. I turn the camera around. So my hot shot is right there, and my Blue M oven is right there. And really, you know, I shouldn't be, you know, I'm just saying. I'm just saying. Okay. Darfishi, welcome. Oh, three-phase. Wow. That's a lot of copper. That's very nice of you to help out. I know you know that stuff cold. Adaptable Innovations, welcome aboard. So, beautiful day in New Hampshire. As you may or may not know, I have solar panels up on the roof. And Friday, I think it was Thursday. Oh, thank you very much. Thursday, we had a record day. I should say an absolutely optimal solar day. Oh yeah, Stan, I love the oven. It's you know, nothing wrong with it. But you know, I'm just saying. Hey, there's Marvin Groeb. Welcome aboard, sir. So Marv and I communicated earlier, so he's all set to join us in a little bit to be our guest for today's live. Yeah, getting back to last Thursday, we had an optimal solar day. Yes, it is a grid-tied system, no batteries, and we just traced the most magnificent, perfect curve on Thursday. They don't come that often, and that was basically 70 kilowatt hours generated. Tarsha Metalworks, welcome aboard. MKL Design, welcome aboard. Hi, guys. So, yeah, great solar day. Temperatures are coming up. Snow is melting. So this morning, I couldn't sleep last night. Just ideas flying through my head. So I was up at 5:30, which I know for some of you guys is normal. For me, it is totally not normal. And I go to the kitchen and I'm start making my tea, and I look out the back window and I have 7 deer in the backyard. and 6 of them were focused on the bird feeder, which I have told my wife is not a bird feeder, it's a deer feeder, and they really like bird seed. So we're gonna have to do something about that because we've been feeding the deer, and that's just not right. And then my wife showed me 2 power walls. Oh, that's pretty cool. Yeah. So Stan, I looked at batteries in our system, and it was not. There was no reason to do it. We don't have time of day issues with energy usage, and the costs were crazy. So we're purely grid tied, and very happy. Don't get me wrong, very happy with that. So yeah, so the deer were in the back, the deer were in the front, the deer were all over the place today. I think they like the weather too. So give you an update on what's going on around here. Things have been great. Some interesting developments in the world of oh, hi Vivian. Vivian is a friend from Taekwondo. Welcome aboard. So we've been playing with the Formlabs resin printer, and we've been making custom coolant nozzles, which are on the website now. I don't know what my rates are per kilowatt hour, Fad Cater. Can I get back to you on that? I'll take that as homework. But I will tell you this. When you generate more power than you're using and you push onto the grid, you get credited at wholesale. You know what's coming, right? But when you use power off the grid, you pay retail, of course. So when the sun is shining, we try to run the shop and run the dryer and use up do our electric stuff when the sun shines. So we put the new NOZs, that's our trade name, the NOZ, the NOZ, our new custom nozzles on the website. You could read about it as noz.gg. Oh, there you go, Indiana John. 19 cents a kilowatt hour. So I sent some out, and one of my beta testers sends me a message, and ultimately a picture that showed he's not using quarter wave class coolant line like I am. They're using half-inch class, which is not unusual for bigger machines. So I've also whipped up a half-inch class lock line style nozzle that's the NOZ 3. It's a 3.3, so 3 inches wide, 3 inches to the focal point, and it has a half-inch. That's in beta. If I get the thumbs up from my beta testers, that'll show up on the site also. So that's starting to take off. The NOZ line is pretty interesting. And it's really cool from a manufacturing standpoint because it's going from, it's going right into a resin printer, printed in the resin printer, cleaned up, inspected, and shipped out. So Indiana John says, I know you said coolant nozzle, but it sounded like Cool Whip nozzle. Whatever you want. We manufacture things. Whatever you like. If you want a Cool Whip nozzle, we could do that too. Almost Machining, welcome aboard. Your package, sir, is ready to ship out. What's the flow rate on the quarter? So I don't know how to answer that. I run it at full throttle, and it's perfect. And I use it for grinding the stones. And one of my customers, one of my beta testers, who I think you already know, is Adam Demuth. And Adam didn't think it was enough velocity. So we made up some higher velocity units. I don't think they're available on the website yet. In fact, I know they're not. and I'm waiting for some feedback. I tried them, and they are higher velocity. So we have 2 flavors, so we can talk about that later. But there'll be choices as far as the velocity coming out of the nozzle. Hey, John, welcome aboard. Thanks, buddy. John stopped by and gave me stickers this morning and a gift with his 2 wonderful offspring, and that was really nice. Thanks. So I'm going to try to get more information on the website for the NOZs. I can tell you that the NOZ 2.2, the sum total of the cross-sectional area of the little orifices is approximately the same as a 1/4 inch hole. So there's not a lot of acceleration in that nozzle. Again, I find it fine with my pump. It's great. Yeah, you're wondering for your pump size. I totally get it. I'll tell you what, drop me an email and let's talk, okay? Maybe I can get you in on beta testing the difference between the stock one and the high velocity one. If you buy one, I'll send you 2. How's that? Okay, Fat Rad Cater. Don't everybody get like all whipped up. This is just beta testing. Anyway, so that's the story on NOZs. That's pretty exciting. I'm having a good time. Other investigations that are going on are different ways of designing them. And we're really enjoying it. Spencer Tool and Grind, welcome aboard, the company with the best name ever. So there you go. So NOZs are going out the door for the first time. That's pretty cool. And PFG Stones are doing great. So PFG Stones, I got yet another message about beveled PFG Stones. So we've been working on this slowly. We figured out how to hold the stones for beveling. I just finished the math on what I need to know, what math I needed for programming the CNC machine to do that bevel. Sounds super simple. It's not, and okay, Fat Red Cater. Not ready yet. Okay, no problem. John says, design anomalies and you. What your NOZ sizes say about your personality. You're a funny man. So, yeah, so math is done. And now I have to make a little spreadsheet. And the procedure is going to be measure the thickness of the stone, because that's one of the parameters. Measure the thickness of the stone, put it in the machine, register it at one magic point, hit the green button, and we get a bevel. And the reason it's a little complicated is we're going for maximum efficiency. So if I can get the time down, I can keep the cost down. And that's what's going on with the bevels. When I'm done, the bevel will have the exact same PFG recipe as every other major surface. The only thing on the stone that won't be ground is the ends. And it's going to be awesome. So that it'll be a variant on the stone where you select that you want to bevel. And it'll be one edge beveled, details to follow. So just stay tuned. You don't have to let me know you're waiting for a beveled stone, because I got like a lot of guys waiting for a beveled stone. But just stay tuned and we'll keep you posted on beveled stones. So that was the second thing cooking in the shop. What else? I think those are the major things. It's been a busy couple of weeks, and everything's been going great. A little update on the coolant system for the Okamoto grinder. Hi, CNC welder. That's been awesome. So you're familiar with the. I will show you. You're familiar with the continuous filter system and coolant tank combination for the grinder, and you can see all the refuse coming out there, all the NFG. That's been working super good, and also we have a 5-micron filter. It's an 18-inch. I want to say 5-inch diameter filter, and we just used up our first one. It took 7 months with a 5-micron filter, so we just changed it out, and that worked out great. And I posted about that. The Manual Machinist, welcome aboard. Obsidian Tools, welcome. Obsidian is very important, by the way, if you're killing a dragon. I just want to point that out. So before we bring in Marv Groeb, which will be in a few minutes, and I will check with you, Marv Groeb, before actually, let me just check with you now. Are you with us? Are you paying attention? So Marv Groeb, you can send me the request to join the live, which should be, it's the little camera symbol with a plus sign on the bottom of your screen. Okay, yeah, just hit that button saying you request to be part of the live, and we'll hit it. We'll bring it in a few minutes, okay? It won't do anything immediately. I have to approve it. Little thing. There we go. Okay, perfect. So while we're waiting for me to run out of things to say so we can bring Marv in, if you have a question for Marv or me, doesn't matter, use the question button at the bottom, okay? If you have a question for Marv and you don't have the question button at the bottom of your screen, hold on to it until we start to get rolling, because I'm afraid it might roll off the screen. Let's see. I don't know. I may be running out of things, but if anybody has any questions for me, how's the PhD doing? I just brought him in. What do you mean? Here he is. How's the PhD doing? You know, PhD stands for piled higher and deeper. And I respect that. Anyway, if you guys have any questions for me on mundane things, let it rip. And we'll bring Marv in a few minutes. I'm going to get a sip of tea. Mr. Blodgett, welcome aboard. We here in southern New Hampshire are quite ready to get rid of this white stuff that is surrounding us. A couple of days of 60 degrees and we'll be there. Hey, man. Okay, without further ado, I think we're going to bring Marv in and welcome him aboard. As you may or may not know, well, I'll let him introduce himself, because I'm that kind of guy. Here, you ready, Marv? Tell me you're ready. I'm going to push the button. But you got to tell me you're ready. Lag. Latency. I got to make sure Marv didn't head off to the men's room. Oh, yeah. Okay, here we go. Give it a minute. There he is. Hey, welcome aboard, man.
Hey, good evening.
How are you? It's not evening.
Oh, it totally is evening.
I
At
guess
least in Germany it is.
in Germany it's evening, and I respect that. It's 18 Zulu right now, right? So it's almost dinner.
19 actually, yes.
Oh.
So already shortly after dinner. That's totally fine.
Are we at 19 because I've been
Daylight saving time, I think.
maybe
Yeah.
I've been getting that wrong.
Yeah. How are you doing?
We're doing great here. Having fun.
I'm a bit jealous of the snow. Europe is having like the worst winter ever. Not only politics, but also in terms of snow here.
Yeah.
And I was skiing this morning.
Nice.
Needed a break from the PhD writing, and it's just it's depressing. You look out and everything's like brown and there's only the slopes left. And I mean, it's the beginning of March. There should be 3, 4 meters.
Yeah. So can you tell us what your thesis topic is?
Yes, I can. Um, the topic is called Experimental Investigation of a Ductile Cutting Regime with Geometric Defined Cutting Edge in Sintered Technical Ceramics. And yes, that is a mouthful. It's really
That
long.
is
Um,
you need an acronym now.
yeah, definitely. I tried calling it Kern Ceramic Competence, which would be 3Ks, but the
Not
rest of
good.
Kern didn't think it was funny,
Not a
so I
good
was not
idea.
allowed to do that.
No,
Yeah,
no. That was a good try though.
yeah. Um, yeah. Now it's going well. Coming back to Obsidian Tools question, it's going well. I'm in the last 4 weeks and I'm just starting to feel the pressure. My professor, he didn't tell me last year when I applied for a PhD with him, he didn't tell me that he's going into retirement this year. So I thought I had like 3, 4 years time, and now I basically need to finish by this summer. So yeah, it's fun.
I don't know how I could possibly help you, but if I could help you, let me know.
Thanks, it's appreciated. But this is just something I have to suffer through myself, and it's been pretty cool. In the beginning, I mean, I've basically started writing my PhD thesis immediately last year, once I registered with the university, and I'm just writing it in my free time. So besides my day job, and in the beginning it was kind of hard because the really difficult thing is if you're writing a bachelor thesis or a master thesis, you can get away with a lot of stuff. But on the PhD thesis, well, you have to defend it and they're going to look for every inch you didn't cover. And I spent the majority of last year just like filling the gaps in my research. But at the beginning, what I wrote, like the first chapter I wrote back in May, it was just really bad. And I had this moment at the beginning of January this year. I told my good friend Josh from Hacker Watches Sydney, I told him like today I deleted 30 pages and I seriously deleted 30 pages and wrote them anew because it just didn't fit the narrative anymore. I wanted to have like a red herring you could follow all through the thesis, and now it's getting to be that point and it's starting to make fun and a lot of fun. So that's kind
Good,
of cool.
excellent. I'm looking forward to reading it. Actually, you might.
Oh, it's gonna be in German. Ooh.
Okay.
But
It's
it's
going to be
never too late to
slower.
learn German, so
Well, if you send it to me electronically,
yeah.
I'll attempt to translate it with Google Translate.
It should translate pretty well, so I think that's definitely something we can do.
Usually, I just look at the pictures anyway. So,
Yeah.
well, welcome aboard. So, we have a whole bunch of people popping in. Some questions. Obsidian says, how do the mechanics in ductile machining with PCD tools compare to the mechanics when grinding? That's a great question.
It's a really good question, yes. And basically the secret of, and I'm clicking in the background because I'm fetching some graphics for this, but basically what everything comes down to, and I'm going to quickly turn my camera so I can show my screen. That's a little bit large. What everything comes down to, and ignore the German words, is usually when you do milling or anything, you have the situation on the left side. So your cutting edge has some positive geometry. So this means the rake angle, here it's the Greek letter gamma up there. You're basically like, I always, when I try to explain it to our salespeople and fail very badly in this, I try to have the metaphor of a spoon going through ice cream. That's basically the situation when you're doing real milling with any tool in soft or hard metals. But this is not something you can do on brittle materials. And in brittle materials, what happens is you're actually cutting a chip thickness. So this is your chip below the cutting edge radius and this gives you an instantaneous negative rake angle. And the difference, coming back to your question, between a grinding tool and a PCD milling tool is the grinding tool always, no matter what grinding tool you have a negative rake angle because your grinding grit kinder, the abrasive grit kinder is very, very shallow in its contour. It's not sharp and it's definitely not like a spoon moving through it. And the tools you're using, if you're using real PCD tools, for example, the 6C tools, but there's also other companies making some. In Switzerland, Dixie Poly Tools, in Germany, DTS, and I'm very sure there's plenty of American manufacturers. You can, for example, get from Canada, K&Y has tools that can do this. Chardon Diamonds in America has it. And all of these tools, they usually have a positive edge geometry, so you could actually cut with them. But the way we are using it for the ductile cutting regime is below the edge radius, so it's an instantaneous negative rake.
Very interesting. I like your term, instantaneous rake angle.
Yeah.
Well, so I think we answered that question pretty well. Here's another one. Is Macor, M-A-C-O-R,
Yes,
in the category that is possible to cut this way? And I would like to add to that question, would you please define Macor?
okay. Macor is a class ceramic. So it's very similar to what you have if you have an inductive cooking field at home, from a chemical point of view at least. And it's used in a lot of precision parts because it has very, very high isotrope behavior, very low heat expansion, and the Young's modulus is also very good on this one. So it's a fantastic engineering material for precision engineering applications. I'm pretty sure that, for example, on Heidenhain linear scales, a lot of Macor parts get used for that reason. And in general, every material shows some ductile behavior. And the physical reason behind this is enormously complicated. And a while back, I tried explaining it on a podcast. And during explaining it, I kind of noticed like, okay, I should first talk an hour about physics for this, but it's fun. Basically, and I'm going to try to explain it in very simple terms here, so something might get lost, but I'm going to try. And this is not because I think all of you are stupid, just because this is so mind-boggling even now to me. If you look at any regular material, so let's say a metal, some ceramics, but nothing that is amorphous. So you're not looking at glass. You're looking at something that has a very regular structure, a crystallographic structure. You have the atoms, and the atoms are kind of sitting like ordered next to each other. And usually what defines a metal is that the first property of a metal is that the electrons that are flying around this atom, they can move. Physics talk about an electron gas existing inside that solid state body. And when you have ceramics or you have semiconductors or you have something like Macor, a glass ceramic, you usually have no conductivity. Most ceramics are really good insulators. That's why we use them for insulators. So you don't get that electron mobility, but you also don't get any dislocation mobility. Dislocation is basically a missing atom in that crystallographic structure. And what we are doing when we are doing ductile cutting regime, and don't worry, I'm leading back to Marco now, is we are smashing the material together so hard because we have that negative rake angle, and that negative rake angle is just pushing a lot of pressure onto the material, a lot of hydrostatic pressure, and also a lot of shear rate, which is really interesting when you consider milling instead of turning that stuff. And what happens is the atoms move closer together, and the atomic orbitals, which are the electrons flying around, they overlap. And you get, for a very, very short amount of time, you get conductivity. And not only electron conductivity, but you also get mobility of dislocations. Coming back to Macor, yes, you can cut Macor in a ductile cutting regime. We've done it before. Macor has one very, very bad property, and that is that it's a very good heat insulator. Because a lot of ceramics are actually really good conductors for heat. So for example, silicon carbide, which most people know as an abrasive grit on grinding wheels, has nearly the same heat conductivity as aluminum. Macor instead is a glass ceramic and a really good insulator. So you have to be very careful with the tools. They tend to burn up very quickly because they get very warm, but it's possible to achieve a ductile cutting regime there. I don't think there's any material you can't reach it.
Marv, are you using coolants when you're doing that? Or are you
Yes,
not?
yes, definitely. I'm always using coolant when milling ceramics. I do not use coolant when I'm milling carbide. And the reason behind this is it comes down to thermoshock. The cobalt, the metal binder in carbide, it makes the cut so hot. It's basically impossible to cut this with coolant. But in ceramics, it's always a good idea to use coolant. I have had some contact with a 6C Tools customer who wanted to mill Marcor but didn't have flood coolant. So he only had MQL, and he used an oil-based MQL, and it actually worked decently for the parts he wanted to do. So MQL is also a possibility. Dry with compressed air doesn't work.
So I have to tell you, this is the second time I've heard your explanation, and because when we had dinner together, you in a noisy restaurant, you did the same thing, and it really paints a good picture, and is fascinating. It's fantastic that the mechanical pressure, the instantaneous mechanical pressure, can basically make it a metal.
I think at that point I should show a picture highlighting the difference. So what you can see now on the screen is a picture of silicon chips. So this is monocrystalline silicon. It's actually semiconductor grade. And on the upper part, you can see what the grinding debris looks like. Both pictures are the same magnification. And this is typical of what you expect of a brittle material. You're just tearing out chunks because your abrasive grit, for example, diamond, is harder. And on the lower part, you can see real chips. These are silicon chips, and they have been formed through this process. So that's really cool, I think.
That is pretty neat. That is pretty neat. We have another question for you. Obsidian
Yes.
Tools asks, can you talk a little about the big polished block which was processed with the PCD ball by dragging it over the surface?
Okay, yes. That one is a fun Instagram story. Or actually not only Instagram story. Okay, I have to go on a small detour here because it's just too fun, and I always like to tell what a nice company we are. So I got asked to hold a seminar at an ultra precision manufacturing conference. I was a little bit stumped because usually ultra precision is not what we are doing. Kern is a very well-known high precision manufacturer, but ultra precision is basically when you're thinking about nanometers. And that's not something we do usually. We think about microns and fractions of microns. And I decided to show something we've been working on for quite some time, which is called diamond scribing. It basically means you take a cutting edge, you orient that cutting edge, and then you just drag it along the surface without turning the tool. So basically, you could call it turning with a linear movement. In the US, you still have a lot of shaping machines.
Right.
So it's similar to this one, but we are using a diamond for it. And the fun thing, coming back to that conference, is once the program was finalized, I saw that I wanted to show a head-up display mold made with this technology. And the presentation before me was from Fanuc with their RoboNano. And RoboNano is an ultra precision machine, which was designed to make head-up displays. So I was trying to compete with an inferior machine in terms of precision, with a machine built specifically for that application. I was like, okay, I cannot do this. And this was like Friday, and on a Monday I had the talk. But something most UPM, so ultra precision machines, are very bad at are heavy workpieces, because the machines themselves, they are not stiff. They kind of move like gummy. They are very, very low on the tension and everything, and they have air-bearing surfaces. So usually they cannot take a heavy workpiece. So I looked in our basement and found the largest chunk of aluminum and decided, okay, let's make we call it shiny spark out of it. And it actually worked pretty well over the weekend. And that shiny spark is not as pretty as it looks on Instagram. The compression swallows a lot, especially the top surface, which was the first one I made. There is quite a ton of cam errors in it, like linearization error too large and everything. The sides are looking decently. And the process this is working is we take a monocrystalline. So it's not a polycrystalline tool. We take a monocrystalline tool. We orient that one in our laser. We have Bloom laser in the machine. And that one has an analog readout. So we can basically see the shadowing of the laser. And this makes it pretty easy to adjust the cutting edge so it's completely perpendicular. And then you just drag it across the surface. And the cool thing is you're not limited anymore with feet per tooth, because there is no feet per tooth. So usually when you're diamond milling, and we have quite fast spindles. So on our normal HSK 40 spindle, we have 42,000 RPM, and then you would move at 500 to 1,000 millimeters per minute. So that's a pretty slow movement. That's like this. And in scribing, because you don't have that feet per tooth limitation, you can just go as quickly as you want, because I mean, turning with diamond, you can easily go hundreds of meters of cutting speed. And our machine kind of is very well suited to moving fast and still having good surface quality. So that shiny spark, hey, Kinetic Precision, that shiny spark is actually milled with over 10 meters per minute feed rate, which makes it 10 times quicker than we would enable it in milling. And you have less roughness as well. So that's a pretty cool project. And well, I got to show off to Fanuc that we can actually rough a part. So the first slide of my presentation was like, you only need one machine and we can actually cut metal and not just make it shiny. So that was cool as well.
That's awesome. Yeah, those parts were pretty impressive. I also saw when we had dinner, you showed that little puck that I think that was silicon carbide, was it not?
That was silicon carbide, exactly.
And that part had milling and threading and all sorts of really fantastic processes in silicon carbide.
Yes. Unlike when we were having dinner, I have my computer with me so I can show a couple of pictures as well of everything behind it. And what's really cool is this is the surface on the puck. And this is usually what it looks like when you're grinding silicon carbide. This is already quite the high magnification, 4,400 times under the scanning electron microscope. And you can see there's a lot of small pittings going on. This is basically where the corns break out. And then you look at our process, which is this slide. And this is exactly the same magnification. It's the same blank of material. It's just that because we are milling in a ductile cutting regime, the process of making the chips is actually different. It's not just tearing out a chunk, but it's actually cutting through the individual grains. And obviously there are some limitations. So you can see there's some pitting going on here. And the rule of thumb usually is if the individual grain is stuck less than 10% in the material, it gets torn out, even with our technology. But in the end, it still comes down to a much higher surface quality. So the surface quality of the ground one, and this was ground by experts and not by me because I'm really bad at grinding, was an RA of 0.3. And on the right side, the ductile milled one is an RA of 0.05. So that's 6 times better. And we actually introduce a lot less damages into the material as well. So on the ground surfaces, and this is very much, Simon, I saw your question, I will answer in a moment. On our, so in my PhD thesis, I had to do a lot of material analytics as well. And we did, for example, Raman laser spectroscopy, which is basically exciting the material with a laser and then looking at the reflectancy and the spectrum. And it's pretty cool because on the ground parts, you can calculate the internal stress of the material. And that internal stress is actually not the hardness, but missing the English word, basically the breakage elongation stress, the maximum stress that silicon carbide can actually suffer. So the reason you have so much pitting on the left side and you also have tons of micro cracks is this is the ceramic toughening mechanism. The ceramic, because you're loading it so much mechanically when you're grinding it, it's actually toughening itself by introducing cracks. And in ductile milling, you do not introduce those cracks and you do not have any ceramics toughening. So your material is unblemished afterwards. Now, the fun thing is, and this is a question for you all because I still don't have an answer, if you look at the energy density during the cut, so I'm not talking the energy going into the spindle, but I'm recording the energy with acoustic emission, and then I calculate a power spectral density. The energy in a ductile cutting regime is higher than in a non-ductile cutting regime. And that's really fascinating. Yes, Indiana Jones, tensile strength. That was what I was looking for as a word.
And we have another question that just came in from Simon Perthy. When milling carbide on a kern, is there a risk of carbide going into the bearings in hydrostatic ways?
Well, we've built quite a few machine types in the last 40 years. The ones you can currently buy are safe. I have no idea about the 30-year-old ones, but for example, in a Pyramid Nano or in Micro, we actually evaluated that one. So when we started our ceramics project, I got a project machine, and after 1 year of only milling ceramics, we took it completely apart, swiped all the guideways and looked at the residue under the scanning electron microscope, and we did not find any ceramic residue. So carbide and ceramics are pretty safe on that machine. Also, the hydrostatic oil gets filtered down to 1 micron and the gap size is higher. So it's actually having a hydrostatic machine, and I guess that's one other reason why they are so common in high quality grinding machines, is just because you always flushed out the guideways, you're in a pretty safe spot.
Excellent. That's impressive that under that scrutiny you found nothing.
Yeah.
Pretty neat. Steel Phil says something that I think you don't need to answer because you answered it already. What do you know about
all the Marco people?
For Macor? There is a lot. We talked about that in a little bit. Let's see what else we got here. What are your, Obsidian says, what are your thoughts about spindles with ultrasonic actuators for ceramic machining?
Okay, there's basically 2 ways you can do ultrasonic. One is the one-dimensional ultrasonic. That is actually getting done about 50 miles away from me. The company DMG produces machines with it. I'm not going to say anything more about that company because I'm a nice person. I think 1D ultrasonic is shit. I think it makes, okay, on the internet. I think it makes no sense at all. It's basically like using a jackhammer. Yes, you get more material removal, but the way you get the material removal is just by putting extra energy into it. And to be honest, there's fantastic grinding bits out there. So I can tell you a couple of companies making grinding bits which are so abrasive that you can just compete with ultrasonic spindles. But if you want to achieve high quality, if you want unblemished parts, 1D ultrasonic is actually very bad for your part because you're hammering away at it and introducing micro cracks. And I'm really surprised people buy parts of those machines. The majority of people I know with ultrasonic machines, 1D ultrasonic, they tell me it's either a placebo, so it's nice for the operator. He has a very tough material, then he turns on ultrasonic and everything is okay. Or they just never use it and wish they had a larger tool magazine. There is a second type of ultrasonic, which is very awesome, and that one is called 2D elliptical ultrasonic. Basically, you're not exciting the tool or the workpiece just in one direction, but you're making a elliptical movement. So you have 2-dimensional excitation. And if you tune this one very well, and there's a couple of companies who produce something like this, LT Ultra and InnoLiDAR too, you have very high frequency, about 70,000 hertz. And then the contact time between the tool and the workpiece is so short that you are under the diffusion constant for the individual atoms. That means you have no chemical wear. And diamond tool wear is actually 99% of it is chemical. You do not have any abrasive tool wear on diamonds, in my opinion. It's just chemical. So if you have 2D ultrasonic on a machine, you can do better milling in ductile mode on ceramics, but you can also mill stuff that you couldn't mill with diamonds. So it's used in diamond turning of steel, which is enabled through that technology. So 2D ultrasonic, cool. 1D ultrasonic, I wouldn't get it.
So you're using diamond tools on steel with the elliptical ultrasonic, and is that eliminating the usual problems with diamond diffusion on steel?
Exactly, yes. The contact time between tool and workpiece is so short you cannot have any diffusion.
That's fantastic.
There is a limit to this. If you move your tool too quickly, so if your feed rate is too high or your cutting speed, then basically it's always in the material. And usually the movement it does is basically this ellipse going into the material and lifting off. Now imagine you're moving so quickly forward that on the backward draw, it's still in the material. Well, then it doesn't work anymore.
Gotcha. Matal Engineering says, what are the factors to reach the ductile regime in Macor? Everybody likes Macor.
I have no idea what it is about Macor.
Will regular machines be able to do it?
Okay. So usually most materials have a brittle to ductile transition of a couple of nanometers. So you're between 10 and 100 nanometers usually. Some go a little bit lower, some go a little bit higher. Macor is on the higher end, but it's still 80 nanometers. If your machine is able to take a constant 80 nanometer pass, yes, your machine can do it, but there's not a lot that can.
There you go. Excellent answer. Let's see. We might be caught up. I think we're caught up. So,
Nice.
oh no, there was one question I missed. Did you get to? This is Cody. Cody Gibbs says. Cody Gibson says, "Did you get to spec that project machine? Are there options you would have wanted in hindsight?"
Usually I get pretty large input on all of our machines we make for our applications department. And I basically spec'd that one out. The only thing it didn't have was a 4th and 5th axis. So we are only building 5-axis machines, and one of the only 3 ever built, which are not, I got one as a project machine. So no, usually for ceramics, I tell people to get something to clean up the coolant better. So usually we have those paper band filters, which filter down to 20 microns. I don't think that's enough. There is a centrifugal option, which is, in my opinion, the most important part for that machine. Other than that, it's still a Kern, it's still a universal machine. So we also have customers who mill ceramics in the morning and aluminum at night, and it still works out.
Ceramics in the morning and aluminum at night. I played for that band. So, excellent. Okay, you guys are doing awesome, but we can't let Marv off the hook so quick. So if you have any other questions, put them in the...
Okay, while you guys come up with questions, I'm going to show something else because I've prepared a little bit of pictures. This is a brand new grinding bit. It's a metal-bound grinding bit, actually produced by the company Zecha, and you can really see the crits beautifully under the SEM, and you can see most of them have a negative rake. And this is the exact same grinding bit after 10 hours. And it's a diamond grinding bit. And I don't know about you, but I've never seen a binding which is so tough that you can actually wear down the diamonds before they tear out.
Wow. That's impressive. Now, is that where you think that's a chemical process or a mechanical process?
Yeah. I think science is not completely sure on that one yet. But if you look at diamond and how hard it is, diamond has, well, okay, it's a definition question, but diamond has 10,000 HV hardness figures, which is like the hardest material by definition. And most ceramics, so for example, zirconia sits around 1,200, silicon carbide around 2,500, alumina can get up to 3,000. Boron carbide, cubic boron carbide is about 4,500. So everything is much softer than the diamond. So why should there be abrasive wear? But at the same time, a very good check to whether you can actually mill something with diamond or grind it with diamond is just check whether there is a chemical compound easily available at room temperature with this. So with iron, for example, steel, well, you have FEC, which is steel. Obviously, this doesn't work. And if, for example, you wanted to try cutting pure tungsten with it, well, there's tungsten carbide, which is our carbide cutting material, which also exists. And well, there's silicon carbide, and silicon carbide always has small amounts of just silicon in it, amorphous. So I think the majority of diamond tool wear is just chemical and thermal, because if your grinding bit gets above 700 degrees, the diamond just goes puff to carbon.
So, I would think that the coolants used during diamond operations are critical.
Yes, definitely. Something I always wanted to try was like super cooling down the coolant. I think there could be a lot of potential in this one, but we are getting a machine with a CO2, supercritical CO2 coolant in late this year into the applications department. And this is a spoiler, so I'm really excited about this one. Yeah, so far, the main issue is no matter whether you're using the Celsius or the Fahrenheit scale, going from like room temperature to freezing feels like, oh, that's a huge step. That's like 20, 30 degrees. But well, in terms of chemical processes, you just have to look at the absolute temperature scale, and going 20 degrees down when it's actually 290 degrees Kelvin, it makes no difference. So just chilling down your oil 10, 20, 30 degrees will feel really bad, but yeah, it's not going to work out.
Is,
So something like
is-
CO2 or LN2 will be the solution for
yeah, I
trying
was
this.
gonna bring up LN2 as a possibility. Is there any way to spray that without
Yeah.
blowing
Well,
something up?
no, I mean, it's totally inert, so you're not blowing anything up with LN2. I mean, it's nitrogen. That's one of the most inert.
Blowing things up. I mean, if you have a spray nozzle spraying
Oh, okay.
liquid nitrogen,
Yeah.
that spray nozzle better be able to handle the cold.
Yeah, and I mean, this is something we've been trying to avoid. People ask us from time to time, and it's just like we take so much effort in making the temperature of our machine perfect that it is mind-boggling that someone wants to pour minus 200-degree cold stuff into the machine. It's just like, why?
All right, we have a bunch of questions that popped in. Fad Radcater says, "What machine technology are you most excited about?"
Okay, laser assisted machining. So I think lasers are pretty boring. Like when you look at a cool milling machine and it's slinging hot chips and everything smells like hot metal, that's really cool. And if you have a laser ablation machine, you don't see anything happening and it smells a little bit burnt. But there is a way to combine the two. And it's actually that you can locally preheat the area around your tool with lasers. And it's called laser assisted machining. There is an American company having a patent on it if you send it through the tool, which is really awesome. You can send it through a monocrystalline diamond, so it's just at the cutting tip. There's also a lot of effects when you just take a couple of blue laser diodes and arrange them around the tool and send them through the middle around the tool. And then very, very tough materials, because they get a little bit warmer, get easier to make. And that's pretty cool technology and something I would love to try out. At the same time, playing with high power lasers, workplace safety doesn't allow that. So,
Well, safe isn't always as much fun. Let's see. Are there future? This is Cody Gibson. Are there any future uses or applications of ceramics you can see coming from your research? Possibilities
okay.
being locked? Question mark.
Yeah. I think this is something that is happening right now.
They may
Um,
can't talk about. So
no. I can talk about what is happening. And the problem is, for the last 20 years, finishing ceramics in a mechanical way was basically grinding and then lapping them to a high quality finish. And once you start with lapping or with honing, you're limited in your geometry. This is the reason why the phone cases you can buy from ceramics nowadays from Samsung, why they are basically a flat chunk of ceramics. Well, it's easy to manufacture them. And now you have a technology which is, I wouldn't exactly call it affordable, because you need a very, very expensive German precision machine and you need high quality diamond tooling. But at the same time, you can make a shape which 2 years ago would have cost 10 or 20 times this, because someone would have had to polish it by hand. So I can see watch cases being really made from ceramics, not just injection molded and polished, but like milled from blank stock. I can see a revolution at one point coming to the dental market. Imagine you're going for a teeth replacement, and instead of waiting 2 weeks for your teeth to arrive, they could actually mill it in like 10 minutes while you're still sitting on the chair and you go home with full teeth. That would be kind of cool. And also, I think those ceramic materials and the way we can now work them will lend themselves to machine building. So something we have considered, and it's too expensive at the moment still, but is, for example, making one axis of our machine from silicon carbide, because the thermal expansion is much lower than aluminum, but the heat conductivity is the same. So we could actually make a much more precise axis from this one. So that would be a cool application. And I think you could actually pay for that. If you really wanted to do this, you could pay for it at the moment.
I would love to see a silicon carbide Kern 5-axis.
Well, the Zeiss Xenos, which is the
Yeah.
most precise production environment CMM, they actually have structural parts from silicon carbide. And most ASML machines are also built from both corduroy, which is a technical ceramic, and silicon carbide parts. So it has already arrived, but just at a level where you are not have where you do not have to be load bearing.
Mm-hmm.
Yeah.
Well,
Exactly.
the timing here is perfect. We're coming up to the top of the hour, and one of our participants, Ed Kramer, who, as you know, is a very serious, very focused machinist, and when he asks a question, I take it extremely seriously. So here it is from Ed Kramer. He says, "When are you starting your Kern-made chef's knife product line?"
Oh, yeah. Um, it's a very valid question, because Eddie knows quite a few of my private interests and projects, and I've been very silent about those. I think the next product development starts after I finish my PhD thesis. Before, I don't have any nerves left for that.
Okay. I want one of those chef's knives. One of our last questions, how do you achieve such accuracy for ductile machining, 80 nanometers, on a milling machine? Sounds almost impossible to achieve when I just think the temperature fluctuations from the cutting action.
Okay. It's a very valid question. Well, first off, you need a very, very high precision German milling machine. I can tell you our salespeople's phone number, if you want. Now, basically, it comes down to what we are already doing with our machine. So I don't want to imply that you can reach 80 nanometers precision on that machine. But repeatability on a Kern Micro HD is crazy good. And then I don't really need to reach 80 nanometers, because you need 80 nanometers if you are turning. If you are milling, there is a phenomena called chip thinning. And in chip thinning, and I have everything prepared. In chip thinning, basically what you have, and again, you have to ignore the German language behind it, but if you look at your chip, and here the chip is in a larger view, you always have your feet per tooth, which is usually what you calculate your chip load on. But there is a part where the chip always gets thinner. This is just natural. It's when you climb milling, chip starts big and gets thinner. And if you start basing your cutting data not on the feet per tooth, which in my opinion is actually a very, very bad measurement for chip load, but you base it on your median chip thickness, then you easily approach nanometric cutting conditions. And I say easily on a Kern. We've tried it out on a funnel Grobotrill because 6C Tools has one, and it's possible to achieve that cutting state. At the same time, your chip is so thin that the tool is, if you're leaving that realm, so for example, your median chip thickness becomes too large because there was too much stock left, or there was too little stock left and it becomes too thin and the tool is only rubbing, your $800 diamond tool just burns away in a couple of seconds. So yes, a lower quality machine can achieve it, and I would say the machine precision should be somewhere sub-micron, so 500 nanometers. Repeatability between the semi-finishing and the finishing pass should be something your machine should be aiming for, and that's not a lot of machines on the planet right now.
Excellent. Last question, because we're at the top of the hour, also from Ed Kramer. This one is more serious. How do you like the new Micro CMM?
I have to check where the Pruka Alicona is hanging around here in the live video. Now, I can give you my preliminary impression of this one. So the Micro CMM, for those who don't know what I'm talking about, we got a new coordinate measurement machine at Kern last week. It's an optical one, and it has something called vertical focus probing. And this basically means you can look at a straight wall from above. So the light is coming from above, and you can still measure the whole wall, which is mind-blowing technology. We got that one last week installed. Very, very cool installation technician who answered all of my questions, and I pushed him really hard, perfectly well. So huge kudos on Lugas for that one. The data at the moment looks too good for me. I know optical measurements, and usually they look like a hedgehog. So you have lots of outliers out of the surface you're scanning. And on that machine, it just looks perfect. It's like you're looking at a step model. And to me, as someone who has spent a lot of time with optical characterization, this looks really weird, that it's like perfect. At the same time, they explain the algorithms behind it, and because it's focus variation, they need to do a lot of pixel binning, which obviously reduces outliers. And then, well, the cool thing about optical measurements is you're not taking one single point like you would with a tactile probe. You're taking 3 million points at one point. And if you average this out, you get a very, very high precision. So I'm not saying it's not possible, but at the moment, every time I look at the data I collect, I'm like, wow, this looks fake. Which probably is just my impression.
Is it like they have some filtering on that you haven't found the off switch for?
You cannot turn it off. It's basically the pixel binning. So when they take 4 or 8 or 16 pixels and combine it,
that's
but it looks weird to me. So at the moment, I would say the results look too good, and they really look good. So next week, I will post a couple of shots we're taking with that machine, and it's really cool.
That is awesome. Well, Marv, thank you for joining us today.
Spencer, thank you for having me.
Yeah, I sure appreciate it. This has turned into sort of just a fun once a Sunday thing. I'll get my Zulu recalibrated for next week. Thank you.
Probably next week we are going out of daylight saving time, and then your calibration is good again.
Well, I'll check the temperature of the calibration standards. I think that might be the problem.
Don't hold them too long in your hand. That's always a bad idea.
Well, thanks a lot, Marv. I appreciate you. And Laney Machine Tech says thanks, and a bunch of other people say thanks. So maybe we'll catch you down the road. And let me know if I can help you with anything, like, flat stones. All right. Bye.
I will. Bye-bye.
Right. You take care. So I'll let you click off, and if we figure out how to do that. Excellent. So that was a lot of fun. Thank you, everybody, for showing up. We do this every Sunday at 1300 Eastern Time in the United States. I thought it was 18 Zulu, but I will check and correct myself if that was wrong. If you joined us in the middle, my name is Spencer Webb. I'm with Kinetic Precision. I make precision ground flat stones. You could learn more at pfg.gg. And if you work your way up the menu into the product stuff, you'll see there's other things we're working on. Balancing rings have been out for a while, and custom coolant nozzles or specialty coolant nozzles is something that's happening right now. So have a great weekend, everybody. And you could all exit at the back. Please watch your step and make sure you have all your belongings with you. And with that, have an awesome weekend.